We're very lucky to have two accomplished explorers join us this morning. And I'd like to introduce them before we get into a discussion of the past, present, and future of Mars exploration. I'm going to start by introducing Donna Shirley, whose reputation I think probably precedes her. Donna is the president of Managing Creativity and retired in August 1998 as manager of the Mars Exploration Program after a 32-year career at NASA's Jet Propulsion Laboratory in Pasadena. She also recently retired as director of the Science Museum and Hall of Fame in Seattle, Washington, and is now president of Managing Creativity, serving as manager, educator, speaker, consultant, and trainer on the management of creative teams. Donna joined JPL in 1966, working on the very first unmanned mission to Mars. She was the manager of the Mars Exploration Program and the original leader of the team that built the Sojourner rover. These programs came to splendid fruition on July 4th, 1997, a day that I remember, and I'm sure many of you remember as well, when the Mars Pathfinder and the Sojourner rover successfully landed on Mars. And 2 months later, when the Mars Global Surveyor successfully went into orbit around the red planet. Shirley has written an autobiography, Managing Martians, the extraordinary story of a woman's lifelong quest to get to Mars and of the team behind the space robot that has captured the imagination of the world. Donna has also been a longtime supporter of the National Space Society. I remember when I was just starting at NSS, getting together with her in Seattle and being inspired by her commitment to exploration and her personal dynamism as well, which is clearly one of the reasons why the Mars program did so well under her leadership. So first, welcome to Donna Shirley. I'll just introduce Peter first.
Okay, good.
Our next panelist is Peter Smith, who's the principal investigator of the Phoenix Mars lander, also providing project leadership for that program. Dr. Smith graduated in 1969 from the University of California at Berkeley in physics and later continued his education at the UA Optical Sciences Center, graduating with a master's degree in 1977. Dr. Smith has been employed at the LPL since 1978, and during this period he's participated in many of the seminal space missions that have explored the solar system. I'll list just a handful here. He's been involved in the Pioneer Venus mission in 1978, Pioneer Saturn in 1979. He's done seminal work using the Hubble Space Telescope to image Titan, and was involved in the cameras of the Pathfinder mission. What brings him here today, however, is that last summer, after 1.5 years of proposal development, Smith's Phoenix project was selected as the first Scout mission to Mars after a competitive NASA selection process. The Scout mission is cost capped at $355 million, and I think it's probably longer than that, isn't it? Yeah. And Smith is fully responsible for all aspects of the mission. The spacecraft will launch in August 2007 and land in the northern polar region of Mars in June 2008, conducting science experiments for 3 to 5 months as part of NASA's search for life in our solar system. The Phoenix name recalls the mythological bird that rises from the ashes of his predecessor. The Phoenix mission uses the mothballed 2001 lander with instruments delivered for both that mission and the failed polar lander mission. Yeah, my guess is that it's that you probably took longer than 1.5 years to build the craft. In any case, what we hope to have here is a lively discussion of the past and future of Mars exploration, with perhaps, I think, some other creative observations about the connections between exploration in general and other fields. The format of the program will consist of Dr. Shirley beginning, Dr. Smith continuing, and then a conversation, and also questions from the audience. So please join me in welcoming our panelists.
Well, I feel like the, can you guys hear? Oh, there we go. I feel like the ghost of Christmas past in the Christmas Carol. The Pathfinder mission was very cool, and Peter was part of that, as a matter of fact. He was the PI on the camera, and I'm sure he'll be glad to tell us more about that. It was a very cool camera, done very inexpensively. That's everything a Pathfinder was. And Pathfinder was the first mission that was done in Dan Golden's better, faster, cheaper mode. Anybody remember Dan Golden? And so as Dan called them, the previous missions like Galileo and Cassini he called them Battlestar Galacticas, because they were very large, very expensive. Cassini would just barely fit in this room, 3 stories high. But Cassini is very successful, Galileo is very successful, and they can do a heck of a lot of science. So the challenge was, can you do good science for not very much money? And so the Pathfinder mission was actually done, and also Mars Global Surveyor, which launched at roughly the same time and explored Mars in the same period of time, although it lasted much longer, were done for about $150 million, which sounds like a lot of money, but it's about the same price as the movie Waterworld. Anybody see the movie Waterworld? Was it a good movie?
Yes.
Okay, you really like science fiction. So that was quite a challenge, and Tony Spear, the Pathfinder project manager, was very nervous about how to do this, but it came off. It was amazing. They decided that it was too expensive to use Viking technology for landing, which Viking used rockets to gently land on the surface. And Vikings worked very well, by the way, but in the same year dollars as Pathfinder, Viking cost about $3 billion. And so Pathfinder was trying to do it at just a tiny fraction. Now the $150 million included the rover and the launch vehicle. So it was really, really a challenge. So all the instruments had to be built very cheaply as well. And Peter came up with a very clever, Peter and his team came up with a very clever way to do that, which he'll talk about. They decided, because Global Surveyor, which by the way orbited for much, much longer than planned, for many years as a matter of fact, and was done very cheaply as well, and it used a leftover spacecraft, which is what Phoenix is also using, although Global Surveyor, instead of using the spacecraft, actually was able to use the instruments from the 93 Mars orbiter mission, which failed just as it got to Mars. And one of the reasons that Mars orbiter failed was because NASA was trying to do it cheaply, and they said, oh, JPL, we don't want you to get involved, we don't want you to manage this contractor, just let it contract to the contractor who does Earth orbiters, and everything will be well. So they did. And JPL didn't pay much attention, wasn't allowed to pay much attention to it. And things started getting more and more and more expensive as they found out that it's much, much harder to go to Mars than to orbit the Earth. And so MO, Mars Observatory, ended up costing almost $1 billion, $980 million. And when it got to Mars, radio communications were lost. And they concluded, the review board concluded that the reason that it was lost was because it had fuel lights, and it had to turn on the engines to get into orbit, to slow down enough to get into orbit. When the engines were turned on, the fuel lights were clogged because they were frozen. And when the fuel rushed through, it put so much pressure on the fuel lights that they burst, and it spun out of control. That was, of course, nobody was there to see this, but that was the conclusion of the review board. So everybody decided, well, we better regroup. And of course, we can go to Mars every 26 months, so what are we going to do? Well, Glenn Cunningham, who was chosen as the project manager, he was the deputy project manager on Mars Observer, and he put together a team with what was then Martin Marietta, now is Lockheed Martin, and put together a team and used a lot of the instruments that were on Mars Observer. Some of them had duplicate instrument storage, some of them had to be redone, but they had plans anyway. So they put that together in about a year and a half, amazingly short period of time, and flew it, and by George, it worked beautifully. Let's see, and then Pathfinder, of course, you guys have all seen, Pathfinder was, instead of using rockets to land, they decided, well, we'll use airbags. Nobody had ever done that before, although the Russians say that they actually used airbags to land on the moon. But it's a little murky. I don't know if there's any Russians in here who could talk about it, Soviets who could talk about it, but it would really, we had discussions with them and we were never really clear on how accurate those statements were. But they decided to use airbags. I mean, they work in automobiles, why won't they work to land on Mars? So we put together a team of very young people working on airbags. And the airbags turned out to be one of the biggest problems of the mission because we could use a lot of the same technology that was used on Viking. The aeroshell, for instance, was done by Lockheed Martin Marietta, and it was identical, basically, to the Viking aeroshells, which we knew worked beautifully because 2 Viking landers had landed on Mars using those aeroshells. A lot of the technology was the same. However, we had to keep the cost down so much that it was really a challenge. Couldn't use all the expensive technology that Viking used. For example, it was determined that the the lander would not slow down enough to land safely, so with just a parachute. And we were using the same, more or less, the same parachute technology that was used on Viking. So they found out that they needed to fire some rockets to slow down. And so they used commercial or military rocket engines to slow down. So the way Pathfinder worked, for those of you who don't remember, it flew directly to Mars. Instead of going into orbit the way Viking did, it just used the atmosphere of Mars to slow down. So it dived into the atmosphere of Mars, going about 17,000 miles an hour. Had to slow down to about 800 miles an hour, and then pop these parachutes, and then slowed down to about 120 miles an hour. And then these rockets fired. There was a radar on board, which was another challenge because the parachute, this whole system is swinging. The parachute, what's called the back shell, which had the spacecraft embedded in it. The aeroshell gets dropped out. The parachute pulled the spacecraft away from the aeroshell, and so it was just a spacecraft coming down. And this radar is trying to sense when you're getting close to the ground, but it's swinging. And so it's actually very difficult to do. So there was an enormous amount of numerical calculations and numerical analysis to determine how to do this whole thing. Then when it got close to the ground, the radar says, okay, we're close to the ground. Then a lot of exciting things happened. These 3 rockets fired that were attached to the back shell. So here's the parachute, here's the back shell, and here's the spacecraft hanging down below it, all swinging. So the back shell had the rockets attached to it. The rockets fired, slowed the whole thing down to about 120 miles an hour. In fact, they slowed it down to 0 when it got close to the ground. And so it's all hovering there. Then big airbags pop out 15 feet high to protect the lander on the landing. The bridle is cut, the parachute and back shell waft away, still powered by the rockets, and the spacecraft or the lander lands, bounces, and it went about 2 kilometers bouncing, boing, 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 boing. And it was pretty exciting to watch on the simulations. When it finally stopped, the airbags were pulled in to the sides of the Pathfinder, which was shaped like a pyramid, 3 sides and a bottom. And then the airbags were pulled in so that the whole thing was semi-flat. And then the petals opened up like the flower, and there was the spacecraft, including the rover. Now, it was designed so that if it landed, I get this question all the time, if it landed on one side, it was designed so that it would open up and flop over. If it landed on the other side, it would flop over. But fortunately, Pathfinder landed right on the bottom. Now, another problem was that since Mars Observer had lost communications, they decided that there had to be some sort of communications all the way to the ground. That we needed to be able to see what that spacecraft was doing, so if something bad happened, you could tell, or if something good happened, you could tell. So they put a little radio on, in addition to the main radio, put a little radio on that would go beep and give us little signals to tell us if what the spacecraft was doing. So one of the things it had to do was to, when the petals opened up, we wanted to hear a beep. Well, it turned out it landed on its bottom, and we heard a beep on the very first thing we heard. So even through the airbags and everything, we heard this little beep, and everything exploded. Those of you who saw us on television undoubtedly saw that everybody was very happy. By the way, the television broadcast and the internet broadcast, it was the defining moment for the internet. Somebody told me that the Roosevelt speech about Pearl Harbor was the defining moment for radio. The landing on the moon was the defining moment for television, the human landing on the moon. And the Pathfinder was the defining moment for the internet. There were 49 million hits on the internet. It's unheard of. And fortunately, our education and communications manager had anticipated this, and he set up websites, mirror sites all over the world, basically, so that this stuff would come through. So, we heard this beep, we were very excited, the petals opened up, everything's fine on 4th of July, and then we discovered that the airbag material is bunched up and we can't get the rover off because the rover depended on being able to come down some ramps in the face of these airbags. Well, the airbags were blocking the path of the rover, so they had to send a command, pick up the pedal, pull the airbags in some more, and put the pedal back down, and that didn't happen until July 5th. And so those of us who were interested in the rover, and since I've been the rover team leader for 2 years, I was very interested in the rover. We all got to bite our fingernails for yet another day, but on the 5th, we got the signal that the lander and the rover were talking, and the rover was able to go down the ramp. And one of our scientists, as a matter of fact, had built a movie to do an individual picture from the Pathfinder camera of the rover going down the ramp. Click, click, click. And the first picture, nothing had happened. So we get this picture back, nothing has happened. And then the second picture, the ramp flexes. The third picture, the rover comes into view. And by the sixth picture, the rover's down. We've got 6 wheels on the soil. So that was a very, very exciting moment for us. And fortunately, Peter's camera got really good pictures of the rover coming down, in addition to beautiful pictures that we got later. Now, when the rover was out running around, well, about 2 centimeters per second, the rover had to talk to the lander. The rover depended completely on the lander, unlike the Spirit and Opportunity, which are up there right now. The lander would image the scene. The scientists would all argue, and Peter can talk about how scientists argue, about which pictures to take. You know, where to send the rover. Where do we want to send? What rock are we interested in? Because the rover had an alpha proton X-ray spectrometer on board, which was its main science instrument. And so it had to get up against a rock and push this spectrometer up against a rock, and that would tell you the elemental composition of what the rock was made out of. So we had to get to a rock. Well, so the lander would take a picture of the scene, and the scientists would all argue, and then we'd send the picture up so we'd get there at night, in the evening. And the scientists would all argue about which rock to send the rover to. And then when they decided, the instructions would be formatted by the rover driver and sent up to the rover the next morning, and sent up to the lander the next morning, transmitted to the rover, and off the rover would go very slowly toward this rock. When it got to the rock, we'd turn around, because the spectrometer was on the back, and put the spectrometer up against the rock, and then send the data back. So it was a very slow process. Now, the rover depended completely on the lander because the rover was too small to carry a radio that would transmit all the way back to the Earth. So the lander, on the other hand, had a radio that would transmit to the Earth. So the rover had a little modem, a little commercial radio modem. The lander had another one. So the lander would talk to the rover, and the rover would talk to the lander. Now, the modems were commercial because we couldn't afford a flight-qualified tiny radio, and nothing existed at the time. So we bought these Motorola modems for $300 a piece, and Motorola sent us a letter saying, if you take them to Mars, they're out of warranty. They really did send us a letter saying, please don't take these to Mars, because they were sure if the mission failed, then they'd get blamed for it. But the mission worked beautifully, the modems worked beautifully, and it cost us $500,000 to qualify the modems to go to Mars, but we only had to pay $300 a piece for them. So everything was rosy. We got beautiful data, which Peter can talk more about. We got the weather. We saw dust storms. We saw all sorts of interesting things happening on Mars. The rover got to, I forget how many rocks, about 10 rocks, went 100 meters all the way around the lander, and got some spectrometer data. And also the rover's science was that she would dig her wheels in the soil and see how much energy it took to dig the wheels into the soil, and that would tell you something about consistency of the soil. So number one, you could get information to be used in future rovers about how to design them, so the wheels would be able to go over the terrain, but also science about how dense the soil was and how deep the dust was and everything like that. So there was a lot of good science in this little rover that the scientists actually didn't want for a long time. Another interesting thing was that the lander was paid for by the science part of NASA. The rover was paid for by the technology part of NASA. And there was a lot of interesting issues that came up as a result of that, which if you go look at the book, Managing Martians, it's all laid out in excruciating detail. You can buy it here, by the way, and I'll sign it, or you can actually get it on Amazon.com, and you can get it used for $1. And if you get it, be sure to get the paperback, because the hardback is full of errors. Now, I shouldn't say this when you're getting ready to buy books here from Mars, from the National Space Society, but I just have to throw that in. So then, since Pathfinder had worked well, at the same time we were working on the 98 missions. Well, the 98 missions, NASA in its wisdom decided that the 98 missions had to be about half the price of the Pathfinder and Mars Global Surveyor missions. So they were going to be done for a very small amount of money. And on top of that, we were told we had to use this new, smaller launch vehicle. So not only did we have to cut the price in half, we had to cut the mass in half. So we asked if we could just fly 2 orbiters or 2 landers in 98, but oh no, we had to fly an orbiter and a lander, so of course it was much more expensive. You can't get the same synergy that you could if you had 2 identical things. So in 98, we wrote many memos to NASA saying, this is really too hard. This is very risky, and we shouldn't be doing it this way. And but NASA insisted that we do it that way. So JPL bravely forged ahead and tried to do it. So when we launched the 298 missions in the lander and the orbiter, we had problems. In fact, both of them failed. The orbiter failed because when Mars Global Surveyor launched, it's very complicated, there was a broken solar panel, and the solar panel was not straight. And the plan was to use the solar panel to slow down, to aerobrake, to get into, you use the rocket to slow down to get into an orbit around Mars. Then you use the atmosphere to slow down further, a thing called aerobraking, which was first tested on the Magellan mission at Venus. And so that got you into the proper orbit, which was a low Martian orbit. Well, when they launched, they discovered that one of the solar panels was broken and it wouldn't get into the right position. So they had to do a lot of creative technology, a lot of creative engineering and thinking about it to make this work. And finally they came down to what they would do is they would get into an orbit much slower, get into this low orbit much slower than they were planning on doing. So it took an additional year to get into the proper orbit, which meant that the Mars Global Surveyor operations basically overlapped with the Mars Orbiter, 98 orbiter operations. Now, the people, in order to save money, and this was my fault, in order to save money, we had combined the operations so that the same people were going to be operating all the missions. But that was planned on there not being anything wrong. You know, nothing will go wrong, go wrong, go wrong. And when the Mars Global Surveyor had its problem, the people who were going to be supposed to be training to operate Mars Climate Orbiter actually were working on MGS and not training. And so when it got down to trying to get the orbiter into orbit, it turned out there was a communication problem between the contractor, Lockheed Martin, and JPL, which was doing the navigation. And the contractor sent commands to send the information about how long to burn the engines and so on to JPL in feet and pounds in English units. JPL assumed that they were metric units, which they were supposed to be, and it fired the engines the wrong amount, got into too low an orbit, and crashed. So that was the end of the orbiter. The lander had an even more difficult problem, is in order to save money, they only did one system test, and the lander was using legs like Viking used to land. And so they opened up the legs, and then there were going to be sensors, and then they were going to fire rockets to slow down. There were going to be sensors on the legs that would sense when you touched down, and then the motors would be turned off, the engines would be turned off. Well, when they ran the system test, they discovered a broken wire. And so they repaired the broken wire. They didn't rerun the system test. Turned out that the broken wire had masked a software error, which was not discovered because they didn't rerun the system test. And that software error resulted in, when the legs were opened up, the sensors fired and turned the engines off 100 feet above the ground. And so the lander was lost. Now, there was some learning that went on from that, fortunately. Dan Golden finally admitted that he had pushed too hard to get the cost down. And that, you know, you can't do everything on the cheap if you want to do that. So for the 2001 mission, which was also planned to be an orbiter and a lander, done even more cheaply than 98, and they canceled the lander, and it was almost done, so they put it in storage, fortunately for Peter, and which he'll talk about. They put it in storage and just flew the orbiter, put all the money into the orbiter, and it worked fine. Mars Odyssey is still orbiting Mars, bringing back terrific data. Then in the 2003 missions, they decided they were going to fly 2 rovers instead of just 1 rover, and that these rovers were going to be very capable rovers, and so they put lots of instrumentation on them, and they freed them from the lander, whereas Sojourner, Truth, the Pathfinder rover, is completely dependent on the lander for communication. Spirit and Opportunity are independent, and they've been roaming across Mars, getting absolutely terrific data, operating much longer than was planned. And in fact, Spirit just found evidence of water in Gusev Crater, which it hadn't found before. And maybe Peter can talk a little more about that, because he's the scientist in the crowd. And I was hoping Bid Boba was going to be here, because he was the one that wrote a couple of books about human missions to Mars, Mars and Return to Mars, where they found not only water, but life. And so I was hoping that Bid was going to talk more about that. At any rate, so the 2003 missions have a lot more instruments on board. They're getting a lot more science data, and it's very exciting, and I submit that everyone should be on their internet at least once a week looking at the science results back from Spirit and Opportunity. By the way, Sojourner Truth, which was the name of the first rover, we had an essay contest, And kids from all over the world submitted essays, and the Planetary Society went through the essays, and we had a group from JPL and the Planetary Society, and we came up with a list of 10 names. We sent those off to the technology people at NASA, and they picked Sojourner Truth as the name, because I had specified that it had to be a woman heroine, it had to be a female heroine. Now, the guys on the team grouched a lot about that, but I said, you know, all the previous spacecraft have been named for men or for, you know, like events or something like that, so we're going to name this one for a woman, and it turned out to be very good. And then, so the 2003 missions also had a name contest, and a little girl, 8 years old, won the contest with Spirit and Opportunity. So that's what's going on now, and I think Peter should talk about what's going to go on in the near future, and then if you want to talk about the far future, we can both do that. Peter?
Thank you, Donna. Donna, you give me a long list of topics to talk about here. I think I'm going to ignore most of them. But,
Okay, lost him.
let me start out by saying my background is somewhat unique in space, in that I have both an engineering and a science background. Engineering in the sense of optics and science and planetary science. And I spent most of my career studying planets with very thick atmospheres like Jupiter, Venus, and Titan. And it was only in 1992 that I had an opportunity to do something with Mars with that little skinny atmosphere that wasn't so scientifically interesting to a lot of us. However, because of my optics background, I was able to propose to build a camera on Pathfinder. And it was based on an instrument we were designing to drop through the atmosphere of Titan. And this happened in January 2005. The descent imager on the Huygens probe took pictures for the very first time close up of the surface of Titan, and found out that it looked a lot like the coast of Italy, with rivers and what looked like a dry lake and some other things that were really quite surprising. And that's really the nature of exploration, and the reason that, you know, I think many of us are so excited about going to Mars and understanding Mars. And really, it's the truth of Mars is what we're after. It's not so much the quarrels between scientists, but we all have the same goal. And that goal is, what is Mars really, what is its history? What are the treasures that are hidden within Mars? And Bob Zubrin, of course, is trying to get humans there to really get quickly to the truth. But this is not going to happen, I think, in my lifetime. So my goal is to get instruments on the surface of Mars that are going to get to the inner truth of the planet, and particularly to try and make progress on this search for life on planets beyond Earth. So the Pathfinder camera is based on the DISR instrument, which had developed CCD detectors, which are not common in the early 90s, in 1990 or 91. And we were able to develop a 1/16th megapixel camera that took pictures in a mosaic style, and you could put them together to make a panorama. And this is the type of technique that is used on the rovers today even. So we are building on heritage, and I think this is a message that was started by necessity out of the Dan Golden era of faster, better, cheaper, but it's really, I think, allowed us to get to the real kind of penetration into the Martian secrets that we have today. It's this building on heritage. And so when Donna talks about the loss of the 98 lander and the mothballing of the 01 lander, Phoenix is the resurrection of all of this investment for the last 10 to 15 years into one mission that can still be done at low cost. And I think perhaps future missions won't use so much the technology and the actual hardware that we've developed as perhaps the processes we've developed to make sure this old equipment that we're flying actually works. And the processes are really profoundly informative as you go through checks and balances on each step of the assembly and test process. And I think that's what we're going to be pushing forward in the future, because the hardware is really great. obsolete by now. But Phoenix is using the O1 lander. It is using the instruments that were developed for the O1 lander and the instrument concepts that were flown to Mars in the 98 lander. And so by using all of this heritage, we're able to keep our costs low, and we were able to win the first Scout proposal. And the Scout proposal opportunity brought in 25 different proposals from the community, 25. And they did everything from flying airplanes to having little robotic grasshoppers around the surface of Mars, orbiters, landers on the polar regions and the equatorial regions, even missions that would skim through the atmosphere and return samples to Earth, the Poor Man's sample return mission. And all of these things were competed, and in December of 2002, they selected 4 proposals for the final evaluation, of which, of course, we were one. And this was really a competition, not unlike in the sports world, where you have the Final 4 in the NCAA basketball tournament. We were very competitive, and over the period of 6 months, we really tried our very best to stand out among the 4 proposals. We all knew who we were. We were all associated with Lockheed Martin, and we're all associated with the Jet Propulsion Lab, so you know the rumors were right. And in August of 2003, we were selected. So we've had 4 years of development since our selection. It culminates in our launch in this August at the Cape. And of course, anybody who happens to be at the Cape, August 3rd, will see our launch. It's at 5 in the morning, night launch. That should be very beautiful. And what are we going to do when we get to Mars? Well, our goals, as you can see in this slide, are to go back to the old landing technique of a propulsion landing. And this is really, I think, the most dignified way of going to another planet. I think bouncing onto a planet like a basketball is not really the way to do it. Can you imagine aliens landing on Earth and bouncing down the street and landing up in some little ditch somewhere? Really not the way to do it. So we are using thrusters, and we have tested these thrusters because we had this spacecraft built at the beginning of our program. We started out with thruster firing tests. And I think we have gone from the high-risk position that we had certainly during the 98 lander, which is our sister ship. We've gone from that very high-risk position through 4 years of hard work and tests down to an acceptable risk position where we really feel a lot more comfortable, although not certain, but a lot more comfortable that we can actually do the really tough task of landing safely on Mars. And our goals once we get there are to land in the polar region where the Odyssey spacecraft in 2002 discovered water ice near the surface. Not just a little water ice, but it's really 70–80% of the upper 3 or 4 feet is water ice. This is something that's never been done before. Nobody has ever landed on Mars and actually followed the water, which is the NASA motto for Mars exploration, and actually found any water. You know, maybe there's a little bit bound to a clay or something, but we are going to get our robotic arm a scoop full of this icy soil, and we're going to do a complete analysis with our science instruments on our deck. So we want to know, in particular, has this ice melted over time? And we will see the effects of the liquid water on the chemistry and mineralogy of the soil that's associated with the ice. And there's some very definite techniques for doing this. We want to know how the atmosphere interacts with the surface, because we see the atmosphere getting wet and dry seasonally, and we think it's coming from this ice. And we want to know, does this represent a habitable zone? As Bob Zubrin pointed out, Mars is a very likely place in its early history. I mean, after formation, when it cooled, in its early history, life could have formed there under certain conditions. And if so, we would expect that there be some sort of residual signature of this type of life form. And we are taking that step of not analyzing DNA or looking at different proteins or counting the amino acids. We're not doing that. We're only looking to see if there's complex organics associated with the environment. Is there liquid water? Are there complex organic molecules? And are there the lack of hazards that would completely destroy these things? And that's what we call a habitable zone. So if there was life there, we might not know it, but we would know that conditions were good for life. Next slide. So those are the big questions. In ancient Mars, did we have a situation where life could have developed? Can we see, is the Martian Arctic the place where it's preserved? On the Earth, organic materials are preserved for millions of years in the permafrost in the Arctic region. I mean, you can actually melt some ice and find the woolly mammoth still in there, and I've heard stories that you can actually cut off a steak and cook it for dinner. So things are preserved in the Arctic region on the Earth. Are they preserved on Mars? How does the water change the soil? This is what we'll be looking at. And what about the interesting polar climate? How does that affect the ice near the surface? So we're the first mission to actually touch water on Mars. And we think of ourselves as a stepping stone to future exploration, and not as an end-all sort of mission. And I think it's the future exploration that's part of the theme of this panel discussion. And so certainly NASA's highest goal is trying to determine if life ever developed on Mars. And organic molecules are an important stepping stone in that discovery. Next slide. Oh, that's a nice picture. Well, if you look up this web address, you'll see a nice picture. I'm going to talk at 2 o'clock this afternoon, and we'll have this slide fixed, and we'll have a complete discussion of our site selection process. But basically, we're landing between 65 degrees and 72 degrees latitude. We don't want to go any further south because we don't think we'll be able to dig to the ice. If we go further north, the solar power is not enough to give us the length of mission that we desire, which is about 90 sols. Well, let's try another slide. So here's an artist drawing of our lander on the surface, somewhere around 70 degrees north latitude, ice near the surface. We're just digging through the soil with our robotic arm, and we're getting ready to provide samples to 3 different instruments on our deck. We have a camera that watches the operation, and we have a weather station. So we have a complete set of tools to dig down to ice, to try and understand the chemistry, mineralogy of the soil and ice, and look in particular for evidence of a habitable zone. Is there another slide? Yes. So here's 2 pictures of a C-17, and the top one shows it in Denver with a big box behind it, and that's the Phoenix lander being sent off to Florida. The bottom picture shows it arriving at the Kennedy Space Center on May 7th. It's only a few weeks ago, and we're getting ready for August 3rd launch. 1 year from today, we would have just landed on Mars. We would have landed 1 year from yesterday, so we'd just be starting to flex our arm and getting ready for action. So it's happening this year, and I really encourage everybody to pay attention to this mission. I think it's going to be quite exciting. And as far as the future goes, I think there's a very big development at the Jet Propulsion Lab now for the Mars Science Lander, MSL, and it's launching in 2009. And then the next opportunity, there's a scout mission that will be some sort of aerometry experiment, an orbiter that's looking at the upper atmosphere, and particularly for gases that are out of balance with the planet, and those often indicate signs of life. For instance, oxygen on the Earth is an indicator of life, and methane on Mars could be an indicator on life. And after that, there's a communication orbiter that will be placed into service, and that'll support the next decade or so of landers and orbiters with a high-speed communication link from Mars to Earth. Really, we're extending the internet to an interplanetary scale. So this is something that will be happening, I think, in the next decade or 2. And then finally, it gets a little murky because there's going to be many administration changes between now and then, and who knows what the plans will become. But there's a lot of opportunities for astrobiology landers, for different types of things that people have envisioned it, so nobody's too sure about late in the next decade. And then the following decade, as has been pushed off each time that the plan is discussed as a sample return, people would, and the science community would love to have samples in their laboratory. They can do a complete analysis. My particular feeling is wait till you know which samples you want to bring back to give you the best chance of finding life signatures. Those are the ones you want to work with. So I think I'm at the end of my remarks, and I'd like to open the discussion to the rest of the room. Thank you very much.
Heather, excuse me. One question for each of you. For Peter, do we plan on landing any lander that will have to be able to do coring samples? And for Donna, I like the book. I wanted to know if you managed to ever export your self-membrane knowledge of management to anywhere else in NASA.
The first question was about coring. Is that what it was?
Have you ever landed? Are you ever going to land something that will do coring samples?
Coring samples. Well, I personally don't know, but it's something that's being discussed a lot. I think the subsurface of Mars is really an area that needs to be explored. And I'm not sure how deep you need to go. It's been pointed out that you go deep enough, just like on the Earth, if you drill a well, as you go deeper and deeper, it gets warmer and warmer. So at some point, you're going to get to a condition where liquid water is stable, and it'd be nice to know that you have the capability to dig a well and find liquid water. This is a resource that would be of great use to future missions. I don't know of any plan in NASA for actually doing this, but it's certainly been talked about, and those type of drills are being developed.
Yeah, managing creativity is what's on my card, and that's the management process I came up with over years and years and years, and applied on the rover. And I have taught a class called Managing Creativity. I taught it at JPL a number of times. I taught at the University of Oklahoma for 4 years as a freshman course and a senior course, and I teach it at various, I give seminars and speeches and things like that. So it's around. And there's a book online called Managing Creativity. So if you go to managingcreativity.com, you can see the first couple of chapters of it, and you can send me $10, and then I'll send you a PDF file if you really want it. Also, I wanted to comment that all of this that Peter and I have been talking about, as Peter mentioned, is part of a Mars exploration program, which Steve Squires, when he was running the Science Working Group, early in the days of when they decided to start a Mars exploration program, which was just after the failure of the Mars orbiter, Mars orbiter, and they came up with this follow the water strategy. And so the whole idea was, rather than trying to go like Viking and find life, when you have no idea what life looks like on Mars, if there is life on Mars, where to go, and all that, would be to have a series of missions that would kind of narrow down. And so Pathfinder proved that it's possible to land on Mars relatively cheaply. Mars Observer proved that it's possible to orbit Mars, get good data relatively cheaply. The 2001 lander is going to show that it's possible to get information about water at one place where we know there's water, near the poles. And then the science lab will get additional information and so on. And this is all part of a Mars exploration program strategy where each mission builds on the information from the previous mission, whether or not it's successful. By the way, I wanted to mention that Mars Express is a European orbiter, which is really getting a lot of fantastic information, and their radar also showed signs of water at interesting depths. And from Mars Global Surveyor, there's pictures of the craters where you can see water or something, some fluid, seeping down the walls of the crater, which some scientists still argue is sort of like, is there creation versus evolution sort of argument. What could it be besides water? People argue plathrates. What else do they argue? All sorts of strange things. Anyway, I think it's water. And there are missions planned for the future. I mean, NASA is looking at human missions, and there's an organization called NIAC, the NASA Institute for Advanced Concepts, where they have looked at human missions. Penny Boston, especially, has looked at what you have to do to lava tubes to make them habitable for people, seal them off and make it so people can live in there. But one of the missions that these missions are trying to accomplish is to identify sites where it would be useful to send humans. I mean, Bob Zuber talked about if you'd want to do several missions before you decided where to invest all those resources. And that's part of what the Mars Exploration Program is designed to do.
I was wondering what kind of data rates you were talking about for the 2011 communications orbiter.
I'm sorry?
What kind of data rates you're talking about for data return from the 2011 communications orbiter? And how does that compare to current orbiters like MRO?
I don't know the data rate. I've been gone for almost 10 years. I remember behind the times. But it'll be high. I mean, already Mars Global Surveyor has returned more data than all the previous Mars missions put together. And when we get that communication network up there, part of it, so you can actually talk to the orbiters all the time, and the orbiters can talk to Earth all the time. Right now, that you can't, when the orbiters are on the other side of the planet from where the landers are, the landers can't talk to the Earth when Mars is turned around. And Mars, as you know, is a 24-hour, 37-minute day. So having the orbiters there will allow constant communication, and it's going to be a potload of data.
Can we expect a video instead of just pictures?
I'm sorry.
Can we expect a video instead of just pictures?
Yes.
Oh, real-time video? Sure.
Mars Science Lander has video on
Now, it probably won't be 24 hours a day.
it. But they have a nuclear power plant, so radioisotopic generator, and
Yeah.
they'll be able to operate without regard to the sun.
Peter, harkening back to surveyor days, if you get 90 stalls out of your mission, would you give any thought to if there was some propellant left? And I do applaud your dignified way of getting to Mars. If there's any propellant left, would you consider doing a hop maybe with the Phoenix lander to another site?
Well, that sounds a lot of fun. Unfortunately, there's no heaters on the tank. Well, there are heaters, but we don't have enough power to keep them heated. And hydrazine has sort of the same properties as water, so it's going to freeze. So once you land, we have to be careful with that extra fuel that we actually eject it out of the pipe so they don't burst as the hydrazine freezes.
Yeah, let's take one from over here.
I'd like to get your thoughts on commercial space in relationship to Mars. There's been a lot of successes, opportunity, spirit, but these have all been normal government industry contract relationships. I'd like to get your thoughts personally on commercial space, i.e. the outside the box of the normal government contract relationship.
Well, it's hard to see how you're going to make money even from the moon. So it's really hard to see how you're going to make money from Mars. Now, Kim Stanley Robinson wrote 3 books, Red Mars, Green Mars, Blue Mars, where he came up with some sort of economic system which I don't understand, which had people making money from Mars. But it's going to be hard to do, at least in the near term. So I think the driving force for people exploring Mars is going to be, the question: can we expand to other planets? Are there places to live? Can we actually live there? And National Space Society is one of those organizations that's kind of looking at that whole issue. That's what the Mars Society is all about. Can we afford to go to Mars and live there for a reasonable amount of money? There's a book by Terry Bisson that I can't remember, it's a science fiction book. I can't remember the name of it off the top of my head, but it's about people who are making money out of movies going to Mars. So it's possible, but I don't know how.
Well, I think that commercially to run your own private mission to Mars is prohibitive, but I wonder if there could be a partnership between NASA and the commercial world where they could contribute sort of packages to a mission, and therefore not at full cost, but could certainly do some very interesting type of things with kind of buy or ride to Mars. So I don't think
It could be an external package, where the test data could be sold, or external results could be sold. It could be an ion drive, it could actually get you there, it could be leased instead of bought, those kinds of things.
Well, one thing we're sending on our Phoenix mission is a little mini CD that actually has a library of books on it. And the idea is that you can preserve something on the surface of Mars for, oh gosh, 1 million years, 2 million years, whereas on the Earth, who knows what's going to happen in 10,000 years. So if you wanted to preserve knowledge, for instance, the Earth isn't the right place to do it. I think you could send it to the moon and Mars, some sort of package of the great accomplishments of the human race.
Thank you very much.
Is there any chance we'll see audio microphones or something audio receiver on Phoenix or future missions?
Phoenix has a microphone. It's on the descent integer, part of Mike Hanley's contribution. And we have the opportunity to be listening during the descent, and I think it still works on the surface. I was hoping with the microphone to actually hear the arm scraping against, the scoop scraping against the ice. And I think that would be quite interesting to add that extra sense to, the touch and feel aspects.
There was a microphone on the 98 lander that was provided by the Russians and partially sponsored by the Planetary Society, but of course the 98 lander failed, so we didn't even hear the crash.
That's good news, thank you.
I have a question regarding potential, an alternative way of thinking about why we might want to go. Mars has lost atmosphere and water. Are we trying to find out why? I think that kind of question is something that might have an application here on Earth and might have more traction with the future of this planet and public support of the Mars mission if we can tie it into things that might have application here on this planet.
Well, I agree with you 100%. And I think this Aeronomy mission that flies in 2011 is specifically designed to look at the loss mechanisms out of the upper atmosphere, particularly water.
What mission?
It's an Aeronomy mission. It's another scout competition, so there's 2 different missions competing. Of course, one mission is led by the new associate administrator of the Space Mission Directorate. So,
Ooh, is that a little conflict of interest?
a little conflict of interest. He's had to step aside, but in any case, we are very much interested in exactly that question. And there's a mission in 2011 to address exactly what you asked.
Well,
Urge you to emphasize.
in fact, the whole program, the reason it's going along so slowly, let's look for the water, find the water, because we decided that, anywhere on Earth there's water, there's life, even inside rocks in Antarctica and things like that. So if you can, and that's the whole point, is to try to understand what Mars was like in the past, how it changed, why it changed, could it happen to us in the future is one of the big rationales for the Mars program.
Over here?
I just want to say I appreciate the lander approach as well. And I wonder if it causes you to do anything extraordinary to avoid contaminating the samples that you're going to take because of the lander approach?
Well,
Yes.
this hasn't escaped our notice that we're trying to discover the chemistry of the surface, we've just sprayed with rocket fuel. So we have a very pure hydrazine that we're using for our fuel. It's sprayed on the surface in small amounts, and it's very reactive. So there may be some reactions taking place because of this fuel, and that's what we're concerned about. But really, I'm not sure what to do about it.
Well, you're going to be getting down below the surface, though.
Yes, that's right. So we will be expecting the surface materials have this extra feature involved with it.
On the much maligned airbags, actually, they're such fun. I mean, think of these things bouncing along. How can you miss out on fun? They were very careful to design the airbags and the content, and the airbags are inflated with a little jet engine, basically. And so they worried a lot about whether the products of the airbags, when they were deflated, would actually contaminate the soil. And the scientists went through a lot of work with the engineers to make sure that that wasn't going to happen. So they're very concerned about that. The planetary protection adds a lot of cost to these missions. Anytime you land on the planet, you're worried about, are you going to carry life along? Because if you do a sample return mission and you find life and it's us, it would be very embarrassing. That's one of the major concerns. There's an international treaty for planetary protection for exactly that reason. Now, I don't think it includes products like hydrazine. It's mainly concerned with things that can be mistaken for life. But it's a primary concern in the design of all these missions. All the orbiters, for example, have to be in an orbit such that at the end of their life, even if there's a lot of drag from the atmosphere and everything, they won't hit the planet for many years.
Is Mariner 9 still in orbit?
Mariner 9, oh yes, everything that's gone to Mars is still in orbit. Yeah, Mariner 9 had to go through the planetary protection. Mariner 9 was the first Mars orbit, 1971.
Last question.
Yes, can either of you comment about the caves that were recently discovered and announced by the orbiting fleet?
I'm sorry?
Can you comment on the caves that were identified?
This is quite exciting.
The what?
Caves.
Oh, caves. Oh,
Caves.
okay. Sorry. I'm getting a little deaf.
The caves that we're seeing on Mars were discovered by which spacecraft? Odyssey, I think, the Instrument. And they're also seen by a high-rise camera. There's a place on Mars, and it's a little circle that's so dark, there's no reflection at all coming from it. It looks very much like a lava tube or some sort of cave. So there are definitely caves on Mars. The question is, could there be some fractures inside that lead into the cave that actually come from deep underground, and maybe water vapor is trapped into the cave, and you have a kind of environment where perhaps biology can exist. And this is certainly seen on the Earth in many caves. Even those that are sealed from the atmosphere and receive no sunlight do contain their own forms of life. So it's kind of an exciting new discovery. We, of course, can't say what's in the caves. It's just that they exist. It's hard to tell from orbit. That's the importance of landers, is that you can actually follow up on these discoveries.
Well, in fact, that was the theme of Ben Bova's two books, Mars and Return to Mars, is that in a cave, they went down in this cave and found, these bacterial mats and all that sort of stuff which exist in caves on Earth. And so, that's exactly what Penny Boston has been looking at through the NASA Institute for Advanced Concepts, which, by the way, has been canceled by NASA and will go out of business. They don't want to spend $4 million a year on thinking of the future. If I sound cynical, it's because I am. So caves are definitely of interest, and so that I actually hadn't heard that. So that's very exciting. Okay, George has got the hook.
Well, thank you very much.
Thank you so much to both of you, and especially, to both of you for flying in and coming in from far away. So we very much appreciate it.
Oh, by the way, a commercial. If you go to Seattle, be sure and go to the Science Fiction Museum, which has some interesting stuff about Mars.
We have time at all?
Yeah, well,